Hello everyone, in another CMPS 211 session. Today I'll be solving some questions from previous's and maybe some other questions that I came up with. So now let's start with this first question. I'll be solving the questions with you as we go. So I haven't actually looked at these problems before coming to this session, or before recording this session, except if I had solved them on my own before the exam, which I might have, but I don't really know. Okay, so now use strong induction to show that every positive integer n can be written as a sum of distinct powers of 2. Okay, for those of you that know, this is actually called a binary representation. Okay. Okay, so this is some. Okay, when attempting to infer pk plus 1 from b, it says that some. Okay, so they gave us some hints. First, I'll not be trying to look at these hints. I actually scribbled over them before I started, as you saw. But now let's try to solve this. If we can open another page, maybe. How do we open another page? Okay. So, first, what is the question asking? They want us to show that every integer n, I believe that they said positive integer. Yes, okay, so for every positive integer n, we should prove that it can be written as a sum of multiples of 2. So like I can find some like n power x1 plus n power x2 plus 2 power x3 plus 2 power x4 for some x's, positive integer xi, okay, where xi is some positive integer, such that okay, so yeah, n equal to this. Okay, so how can we write this in other words? Okay, so like for example, let's say what this is saying is like, for example, 5, I can write 5 as 2 power 0 plus 2 power 2, 4 plus 1, right? That would be 5. We want to show that for every number I can come up with such a representation of just powers of 2 that are summed with each other. Okay, so just because I might, just so that you know what the binary representation is, this can also be written as 1 times 2 power 0 plus 0 times 2 power 1 plus 1 times 2 power 2, right? Because there's a 0 here. Binary representation is the same idea. So this would be 5 in binary representation. Okay? Because you have 2 power 2 and 2 power 0 and 2 power 1, right? So yeah. Okay, so now how would we prove this? This looks like an induction problem. Why does it look like an induction problem? Because if I could represent all the numbers up to like some positive integer 2n minus 1 maybe, okay, actually 2n minus 1 would always look like this, like some series of 1s. You could try to think about this yourselves, why this would happen, but yeah. So if I could prove it for that, how could I prove it for the next one? Because it looks like a repeating problem, you see. If I could represent some number using binary or using this form, then I could just extend the string, maybe, as I showed you, the binary string, this string. I could maybe I've said that for any number up to, can be like all the numbers that can be represented in this range, like with n bits, with n ones and zeros, all the possible combinations. How could I add, if I added 1 bit, what are the numbers that I could represent? Okay. I hope this makes my line of thinking clear. Now let's see. Okay, so assume that I can represent all the numbers up to n minus 1 for some n, for 1 up until n, which is like some n. I want to prove it now for n plus 1. How could I prove this for n plus 1? Okay, okay, so let's say that all the numbers up to this number can be represented, right? For all these ends. So if I could represent all the numbers up until 2n minus 1, okay? Okay, so what are the numbers that are greater than 2n minus 1 but are also okay, so in other words, what would this be? This would be just this plus 2 power n, right? So adding this one bit in because it's called a bit in the binary representation, it's called a bit, each one of these. So adding this one, if you will, this one greater power of 2 should make me able to represent a number that is 2n plus 1 minus 1, right? So what am I trying to prove again? I'm trying to prove that if I can represent all the numbers up until 2n minus 1, then I could also represent all the numbers up until 2n plus 1 minus 1. Okay? So let's see. If I can represent all the numbers up until 2n minus 1, then for each number greater than x, that's right, it's greater than 2n minus 1, but it's also less than, so it's, sorry, the minus 1 is down here. Okay, so for all the numbers x such that x is less than 2n minus 1, I mean greater than 2n minus 1, but less than 2n plus 1, okay, so strictly less than, okay, I could represent this. How could I prove this? Okay, so every number that's in this range, x is less than 2n minus 1, but x is greater than, okay, so x is strictly greater than 2n minus 1, but it's also less than 2n plus 1, the plus 1 is in the power, okay? So it's strictly greater than 2n minus 1, the minus 1 is down, right? Why is this? This is because we're trying to prove it up until this number. So if I had the or equal sign, I would put the minus 1. Okay. So now, and this is all already proven, so it wouldn't matter if I put the or equal sign. Okay. So now, we have this. We said that we want to prove that every x in this range can be represented using powers of 2. Okay, so every x in this range is equal to 2n minus 1 plus some k, right? Because it's greater than that. Okay, but we know that k is less than 2 power n, right? Because if k was 2 power n, it's actually less than or equal to power n, it would be 2 power n plus 1 minus 1, okay? X would be, so then because if it was 2n, if it was like 2n plus 1, if k was 2n plus 1, x would be 2n, right, plus 1, right, without the minus 1, so it would be greater than this, or be equal to this actually. Which we don't want. We want it to remain in this range. Okay. So we know that k is less than 2 power n, and if k is less than 2 power n, what can we conclude? We can conclude that every x is equal to some y, right? Is equal to some ys plus k, and y since y is equal, okay, so actually let me rephrase this, sorry, okay, because there's a better way of saying this. Okay, if we keep the 2n, let's keep the 2n minus 1, okay, let's keep the 2n minus 1, okay, and k, but what do we know about k since it's less than or equal to n? So since it's less than or equal to n, then k can be written as sum of powers of 2, right? Because k is less than or equal to power n, and we used strong induction, right? We assumed it for all numbers up until 2n minus 1, right? We can take the case of unless k equal, okay, so this is actually just like this very side note, but you could also say if k less than 2n, right, then by induction hypothesis, right, I believe. If k equal to 2n, then it's already proven, right, because 2n is a power of 2. Okay, now what? Okay, so now since we know that x equal to 2 power n, right, minus 2 power 0 plus 2 power x1, 2 power x2, 2 power xn, right? This is already a sum of powers of 2. Now, we have two cases because we have a minus 2 power 0, but as you can see, we're already almost there. So, okay, if k is odd, what do we have? If k is odd, then we'd have the 2 power 0, right? We have the 2 power 0 among the powers of 2 in k, right? Because if we didn't have it, then it would be even. Okay, so if k is odd, but this cancels out, right? It cancels out. Now, what if k is even? Okay, if k is even, then are we stuck with a 2 power minus 0? Of course, we're not stuck with a 2 power minus 0 because we have at least one power of 2 that is greater than 1, right? Because we have 2 power n. Okay, so by the way, I didn't write a base case. The base case is trivial. Maybe you could take 2 power 0 or 2 power 1 or anything, yeah. Okay, because you could take your base case maybe 2 power 2, and then this you'd know that n is greater, that 2 power n is greater than 1, right? Okay, but even in this case, now you could take two approaches. The first approach is that you could say that you could prove that any 2n minus 1 is equal to 2n minus 1 plus 2n minus 2 plus la 2 power 0. You could do this. This is actually provable. But we could do something much simpler, which is use the induction hypothesis again, because 2 power n minus 1 was in our induction hypothesis. We assumed it for all numbers up until this number, right? So it was in our induction hypothesis. So yeah, some of you might have noticed that and might have been really annoyed. But yeah, it was nice to point out that you could actually even prove it without using the induction hypothesis. Okay, so now let's see what the hints were. I'm actually curious. Okay, so the first hint is, okay, so treat where k is even or odd. Okay. Now we had a k that we treated as even or odd, but I don't know if it's the same k as the one that they are mentioning. Let's reread the question. Okay, when attempting to infer pk plus 1 from the previous instance, okay, yeah. When k is odd, use the fact that k plus 1 over 2 is an integer. Okay, so they proved it, I guess, in a very different way. The way that I proved it came very intuitively to me, but كمان I guess they used induction. Okay, but let's see. Okay, so they didn't tell you on what you should do your induction, but I'm assuming that you're doing it like n plus 1, n plus 2. Like this is the type of induction, not powers of 2. Yeah. I think the powers of 2 ones might have been much easier, but let's see what they did. Okay, so take first question can be written. Okay, inductive step, assume the holds for all positive integers. Okay, we need to show that. Okay, so if k is even, okay, so they took it by cases, which might be harder. Okay, so without reading it, let's try to do it in their way. Okay, so let's try to do it in their way. Okay, so let's say k is odd, or let's start with the even one. It's easier, I guess. Yeah. لا. Can we make this bigger? Okay, so we can. Okay, so if let's say that k is even, then k plus 1 is odd, right? And since k, okay, this one's pretty easy. K is powers of 2, as we did x1, x2, and then you just add 2 power 0, and that's k plus 1. Okay, this one's easy. Okay, so now what if k is odd? If k is odd, right, then k plus 1 is even, right? And if k, okay, and k could have been written as powers of 2 up until xn. This is k. Now we're adding a plus 1, right? So you added a 2 power 0, but k already had a 2 power 0, right? Because k is odd, then you added these two, then you add these two in that. So you'd add a lot of things. I think that this is actually provable, maybe without using the hint that they gave you. Why? Because you know that k had a 2 power 0, right? And you added another 2 power 0, right? So now you have a 2, okay? So if the representation of k already included a 2, then now you have a 4, and if it only already included a 4, you now have an 8, and you could see where this goes, okay? So it will always have to stop, right? Either it will have to stop because, okay, so we reached 8 and now we don't have this, the representation didn't already have an 8, so it will stop, or the representation would have had everything. In other words, the representation would have been like this, right? So it would have been 2 power n minus 1, as I said previously. And if it's 2 power n minus 1, then what would happen that it would become just 2 power n, right? Because you added a 1. So it would still hold, yeah. But let's do it their way. Okay, so now we know that k plus 1 is even, but k is odd, right? And if, okay, so let's see what they wanted us to do. I think their hint was 2k plus, okay. So k plus 1 over 2 is odd, right? I mean, is even. Is not necessarily odd or even. Sorry. Okay, so k plus 1 over 2 is not necessarily odd or even, but it's less than k, right? So it can be written as powers of 2. Okay, so if it can be written as powers of 2 and then you just divided them by 2, it would be just doing minus 1. So then just multiply them by 2 again, right? And you'd get the original, okay? So for those who didn't understand what I just said, okay, so k plus 1 over 2 can be written as 2 power x1 plus 2 power x2 plus 2 power x3, right? Right, but, okay, so what does this mean? Just multiply 2 on both sides. Then k plus 1 is just the same representation, but with a plus 1 on each power of 2. Okay, so then this would be proved. So like k plus 1 can be written, which is, it can be written in this form. Okay, so it's a nice question. Actually, I might give you a question from my own on binary strings. Okay. Let's try to solve this one first, though. Okay, so use mathematical induction to prove this. Okay, this type of question comes a lot. I haven't solved one of these in a very long time, maybe, but let's try. Okay, so we want to prove this. Okay, so we want to prove this. Okay, so you have 1 over n power I into 2 power I plus 2, right? Okay, so we want to prove that the summation of this for each I up until n is equal to n over 4n plus 1, right? Okay, so let's try to think about this. Okay, so first, what would the base case be? So the base case would be n equals the 1, let's say. So it starts from 0. Okay, so it starts from 1. So it's just one of these. So 2 power 1 into 4, so that would be 8. 8 is indeed equal to 1 over 4 times 2, which is 1 over 8. Okay, so this is the base case. Now, okay, so let's try to prove it now for n plus 1. So if it works for n, of course, remember that I don't really write very formal proofs when I'm doing these sessions. And it's actually, okay, so I mean, in my opinion, the most important thing maybe is to have the logic behind it, but it's also important sometimes to write concise proofs. But I don't know if each year what kind of exact terminology they would be using and what's exact structure, and some professors can be really picky. So I'd actually rather not write concise proofs at all maybe, and then just leave it up to you to know what your professor requires and what level of like abiding by a specific structure and specific terminology they would like. But yeah, okay, so now going forward, we know that, okay, so we've proved it for n equals the 1. Now let's prove it for n. Okay, so let's say that it holds for n. Let's prove it for n plus 1. Okay, so if the summation up until n of this is equal to n over 4n plus 1, right? Then what could I say about n plus 1? Okay, so the summation for n plus 1 is the summation up until n, the same summation, right? But we add to it 1 over 2 power n into 2 power n plus 2, right? Okay, so let's say we added this on both sides. So this would be equal to n over 4 n plus 1 plus 1 over n into 2 power n plus 2, right? So now what? Now let's take a look at this. Okay, so let's see. Okay, so first things first, so that we would be able to add them. Okay, so let's take a look at this. Okay, so you'd be, if you distribute the two, you'd get this, right? And then how could we add these two together? So of course you'd want the denominators to be the same, but we have powers of 2 here, which makes this kind of tricky. Okay, okay, so of course some of you are thinking like, let's multiply on both sides, but what I'm trying to think of is, what if there's an easier way? So now what we want to prove is that this thing over here, this thing, is going to be equal to, now we started on n and we're proving for n plus 1, right? Or n minus, okay, so we want to prove for n plus 1, so we should have had here plus 1s, right? Yeah, so we should have had here plus 1 all the way through. Okay, so and then this would be okay, so then you'd have 2n. Okay, so this would remain the same, but then this, you'd have n plus 1 squared, which is n plus 1 squared is, okay, so let me correct this very quickly. N plus 1, all of it squared, would be n squared plus 2n plus 1, right? Okay, so now what we actually want to prove is that n plus 1 over 4n plus 2 plus that is equal to this, okay, right? Okay, so basically what are we trying to prove? This is equal to n over 4n plus 1, right? Plus 1 over 4. Okay, so then we'd have to add the plus 2 down there. Okay, so I'm just okay. I'm going with you through the question. You could have multiplied the denominators and maybe by now you'd have a solution, but what I'm trying to show you is how I would go through solving this question. Probably if you solve enough of these questions, I remember maybe at some point it becomes second nature. Like there's a pattern. They don't really come up with very like creative new questions, probably so that you could get grades. But they all follow the same pattern and they boil down maybe to the same thing, maybe like this. Yeah. Okay. So now, what this is equal to n plus 1 over 4 n plus 1, but when we added this, it's just another plus 4, right? Okay, so it's like adding a plus 1 and a plus 4, a plus 1 to the numerator and a plus 4 to the denominator. Okay. I hope this is right. Or at least I hope this is, on the right track, solving it in a nicer, quicker way. Okay. So it's like okay, I might actually just go with multiplying the denominators. Okay, so let's try multiplying the denominators really quick, because I don't know if what I was trying to do was going would have like an end, or it would be open-ended or like much harder. Okay. Okay, so it's times 2n plus 1 plus 2 power n squared plus 2n. Actually, it might have been better if we went with n minus 1 and n because of this, but we'll see how it boils down. Okay, plus 1. So then we'd have over here just plus 1. Okay, so basically what we want to prove is that this, like this whole thing is equivalent to this. Okay, let's see. Okay, so let's first start by doing this. I'm distributing the 4. Okay, sorry for the handwriting. I'm just writing the denominator right now. Okay, so let's substitute this with 2 power 2. Okay, so now we have 2 power n plus 3n plus 2 power n squared plus 2n plus 3 plus 2 power n plus 3, right? Plus 2 power n squared. Okay, so this is an n here. Plus 2n plus 3, and you could probably see where this is going. We have plus this with an n, and then we have this without an n, right? And then same for this. So what we do is let's take them in common. So you'd have 2 power n plus 3 to n plus 1 plus 2 power n squared plus 2n plus 3 to n plus 1, right? And now we could take the n plus 1 in common, and then we'd have an n plus 1 above and an n plus 1 below. So the final equation would be 1 over 2n plus 3 plus 2n squared plus 2n plus 3, which is not what we wanted actually. What we wanted was 2 power, okay. Okay, so we messed up somewhere, because this of course is not equivalent to adding 4 each time. Let's try to backtrack. Now maybe I'll go over to the algorithms problems. Okay. Okay, so given a list tuple of integers a, the prefix sum, a is another, okay, develop an algorithm which given a list of integers produces their prefix sum. Okay, so it's really important. Now I'm going over the questions like this. I'm not really reading the question and then I'm explaining, but I really actually even advise you to try reading the questions and seeing if you understand them or not, because it's also of course important to understand the questions in the exam, and it's sometimes a very big problem that people don't understand the questions in the exam. Okay, so yeah, let's see. Okay, so first we want to give the prefix sum. So what is a prefix sum? A prefix sum is, do they want it as an array or, okay, so yeah, so the prefix sum, they want it as an array. So let's see some array, let's call it array R. Okay, so we have this array. The prefix sum of this array would be 0 and then n, and then n1 plus n2, and then n1 plus n2 plus n3, and so on and so forth, right? Okay, so let's try to do this. Actually, not always they include the 0. Okay, so here they don't want us to include the 0. Sometimes, I guess maybe most of the times 0 is included. I'm not really sure. But when I do this, actually I really need this a lot because I solve on code forces again. I'm doing a bit of marketing because I really love this. But yeah, it's really used there. So yeah. Okay, so now let's look at this. So what we want is, given this array, to return that array, right? So if this is, okay, so the first element is n, right? The second element is, it's n1. The second element is n1 plus n2, right? So the third element, instead of saying that it's n1 plus n2 plus n3, isn't it easier to say that it's equal to the previous element plus n3? And doesn't this follow always? So the other one would be plus n4. So we'd use this to write our algorithm, right? Okay, I don't know if they told you of a specific convention to write, but I'll just be writing it in pseudocode, the way that I find comfortable, maybe, right? Okay, so for I equal to 0 up until, okay, so when you're writing pseudocode, you don't really start with the 0 as you're maybe used to in your programming courses. You usually start with just 1. Okay, so before starting this algorithm, I'd say that n at 1, okay, so say that this is 2, n at 1, so s at 1 is equal to array at 1, right? And then for I equal to 2, s, so s at I, what is it equal to s at I? Okay, and of course instantiate an array s of size n. Okay, so s at I is equal to array at I minus 1 plus array at I, right? Why is that? Let's think of it. So at 1, it would be the first element. At 2, it would be the second element plus, okay, so not array at I minus 1 plus, so it's equal to s at I minus 1 plus array at I minus 1. Why? Because the nth element of s, right? This is actually complete. I'm just now proving it intuitively before I go to writing the actual proof and loop invariant, because once you understand how to prove this intuitively, the loop invariant maybe becomes really easy, or once you intuitively understand what a loop invariant is. Okay, so the nth element of s, right, the nth number of s, of the array s, of the prefix sum, we said that it's equal to the n minus 1th number, right, plus array at n. We said it here, right? The nth number, so like the third number in S is equal to the second number in S plus the third number from the array, right? So this is basically what we are saying. Maybe you'd want to take a moment to take this in and understand it really deeply. Okay, so now, can you run your algorithm in place? Okay, so what does in place mean? In place means that you are not using an auxiliary data structure. right? So here we used S. S is an auxiliary data structure. What does that mean? We used another array. Doing any algorithm in place means that you will be producing what your algorithm does without the need of any other thing other than the input, right? As in no other arrays, no other stuff like that. Okay. Maybe you could use variables, other variables, like you could define an x equal to like 5, maybe, but like maybe that still counts as in place. But yeah, but the arrays, this kind of stuff, you don't want to have, you don't want to instantiate new ones, maybe. Okay. So can we do this in place? Of course we can. Actually, it might be more intuitive. Why? Because if we have array equal to this, n1 and 2 up until n, if you want. Yeah. Okay. This would actually imply that the array is of length n squared, right? Maybe because we have n numbers. Yeah. Actually, no, it doesn't imply that. Sorry, it doesn't imply that. But what it's saying is the number of numbers, right, is equivalent. So yeah, the number of number. Okay. So it's not saying anything actually. Okay. So now what they want is to show if we can do this in place. Okay. What does in place mean? In place means in general. Okay. If you ever hear of the term in place. Okay. In place means that you are not maybe using an auxiliary data structure. So here, what does that mean? It means that you're producing the output of your function without the need for auxiliary data structure. Okay. Famously, maybe actually one of the open problems maybe of computer science, if you've taken merge sort, I think it's an open problem to solve merge sort in place. If you actually manage to do so, it would be maybe a very big breakthrough in the computer science community. So yeah, maybe give it a shot. Can you run your algorithm in place? Okay, so let's see. And of course, when you actually solve merge sort in place, don't forget to mention me in your papers. Okay, so expansion again. Sorry for being a bit messy. This is the first time I'm solving it maybe with you. So okay, so let's just do this. This would become a 4. This would become an n cubed. And then we'd also have a I believe that's the last thing I did was I said what in place means. If I didn't say that, it's just basically very quickly just not using any auxiliary data structures. Basically, just use the input to provide the correct output without using any other maybe arrays or stuff that were not given to you in the input. Okay, so this actually might be even easier to think about than the original problem. Why? Because now we could just say for I equal 1 to n, actually 2, because array at 1 will not be changed. Array at I equal to array to I minus 1 plus array to I. Why? Because we know that the first element in S is equal to the first element in array, right? Okay. And then what is the second element in S? It's the first element in S plus the second element in A, right? Okay, but the first element in S is also the first element. So yeah, so now what's the third element in S? So then the second element in S is equivalent to the first element in A plus the second element in A. What's the third element in S? It's the second element in S plus the third element in A, right? Which is now equivalent to the first element in A plus the second element in A plus the third element in A, right? So the first element is already correct. And then instead of storing the second element, we store the first element plus the second element. Now we have the same thing that we had in S. So then we could substitute the third element with the thing that we now have here, which is 1 plus 2 plus 3, right? So each time, so now we'd have array at 1 plus 2 plus 3. Now array at 4 we'd add again to whatever we had. Now we have everything, right? So you can think about it as if you're saving the solution to the problem up until n, right? In the nth element, and then to solve for n plus 1, it's just the solution from before plus this one, right? And this is actually the loop invariant. What's the loop invariant here? It's that the array at I is the solution up until I, right? Is the sum of elements up until I, right? And the same actually is they basically have the same loop invariant, maybe. Yeah? Okay, so a loop invariant. So at the start of each iteration, s at k is equal to the sum of all elements up until k, as we said. Okay, so proof for the algorithm. Now this is not that hard. It's similar to induction, so I won't be really going over it. It is induction, I guess, maybe. But yeah, I won't be going over it. It's not that hard. It's just that you add it up until n, as I said, and then you'd add up until n plus 1. So you'd have the addition up until n plus 1, right? Okay, so let's do the runtime. And runtime is something that gets most people really scared. I might do just another session, very quick one, just on running times, giving you like really tough questions on running time. Maybe like if you solve these questions that I'll come up with later, you'd be really ready to solve any running time problem that you might encounter in CMPS 11. Not really in life, maybe, but in CMPS 11. I don't know if you have for this exam also the running times that like the master theorems and the trees, but these are just really memorization, I guess, so I won't be really going over them. Okay. So in terms of the input size, okay, so now what do we know? We know that we go over each element once, right? So we have a loop that goes over each element and then it adds whatever we had before. So we're going over the element once, so it's O of n, right? So they might prove it in a different way, right? Algorithm executes the runtime. Okay, so they might do it mathematically, like exactly. Don't know, they require you to do this in the exam, or you could just say that it's a for loop that goes over all elements once, and then each time it does O of 1 operations. But you could do what they did. You could do this, like this goes over n minus 1 elements, and then each time I'm doing one operation, right? And then you could do this. You could assign for each one. You could say like this is n, and then each time I'm doing one operation, right? So that would make us have maybe like so if it's n minus 1 things, and each time we're doing one thing, and then maybe they'd count the looping as another thing. So like it would be this equivalent to of n, or like theta n. It's all correct, right? But yeah, this one was pretty easy. Determine the amount of space required by the algorithm in terms of input size. Okay, so I guess when they tell you a space, it will also be of n, because like you even if you created the other array, you didn't do it in place. It's still like 2n, which is of n. But okay, of course, if you don't know, if you had like this, you'd always take the n squared maybe. So you'd always take the higher power. So this is of n cubed. Like even if I have one like this, like 10k or 1 million n, this is still O of n, right? So yeah, now this is if they want it in terms of just like the space in the array. I don't think that they require you to go further than this, but actually even in the running time maybe. I don't really think of this. We say like a plus b is O of 1, which you should consider it can be O of 1 in this course, but like in actuality you have binary strings representing a and binary strings representing b, right? And then you'd have to go over each binary string and like add the bits, and then like if you have 1 make this one, like the output of them is 1 and carries on, you know. And if you already have a 1, then these they carry on, you know. So it's actually, it's not really of n, it's like log n maybe. But I mean, it's not really O of 1, it's actually log n maybe, but you don't really have to care about these things. And the same goes for the space complexity. Like, you are thinking, okay, so we had one array, and now we have, and then we have, and now we still have like one array, or maybe we have two arrays. But in actuality, I had one array like n1, n2, n3, but now my new array is n1, and then n1, n2, n1 plus n2, right? And then n1 plus n2 plus n3. You see, like, each element is almost like, I believe, like, asymptotically, it's maybe like each element, you'd see it n times. So it might be n squared, maybe space, like, to that extent, because I see, like I see the number one, the element n1 n times, and I see the element n2 n minus 1 times, right? And so on and so forth. So yeah. If we assume that all the n's are equal, then this would be n squared, and then it would be n squared times some constant maybe, or like times, so it would be something in the order of n squared maybe of the components, and like something in the order of and also multiplied by something about the sum of all of the elements, something like that maybe, you know. If at least you could say that it's n squared times the max element. I could say the order of that. It's less than that, to all of that. But yeah. But I don't think that they require you to do this. I think they just say O of n, right? In addition to input the algorithm. So yeah, it says O of n. You don't really, of course, in the exam, don't write n squared times that. Just don't write that. But it's nice to know. It's really nice to know. Now this may be purely theoretical. Maybe in your operating system, all ints, it's not like all ints are stored maybe like in Java are 32 bits maybe, you know. Like in a language like Python, maybe like Python doesn't have exact bits for integers. You don't say int or long. If some of you have taken Java, you're familiar with these terms. In Python, it's dynamic. So if so 5 can be represented with 3 bits, but 7 cannot be. 7 needs 4 bits, right? So Python, I believe, maybe gives 5 3 bits exactly and 7 4 bits exactly. You could that makes you able to represent arbitrarily long numbers in Python, which is really nice. So yeah, this is it for this session. I might be uploading another very quick session just on running times, on difficult maybe running times that you might find interesting.